Woohoo! Another practice exam? What? You shouldn't have. How nice of you. Well, thanks for coming. I know we've had a lot of these, and every one we do, we get a little bit better. So step by step, we're climbing up that ladder of understanding and knowledge, and so that when we walk into the real exam, we're going to go in there head high, confident that we're going to do great. And so, let's keep practicing. All right. While you're doing the test, make sure you have your handy dandy table of Laplace transforms, because at some point we're going to encounter some Laplace transforms, and we want to make sure we have our table available. All right, time for us to begin. Our first question. Given that our x sub c is a e to the 3t plus b t e to the 3t is a homogeneous solution. Oh, okay, so good. They gave us the homogeneous solution for free. Wow, that's cool. Oh, sorry, back to the problem. To our differential equation, x double prime minus 6x prime plus 9 is 3t to the minus 5 halves e to the 3t. Use the method of variation of parameters to find a particular solution. Now, I think on this problem we should use the method of variation of parameters, and there's a pretty big clue about why we should do that. It tells us that we should do that. So yeah, that's a very strong clue. There's actually another clue. Namely, this is non-homogeneous, and it's non-homogeneous where the function is kind of not a great looking function. And so you have a not very pleasant looking function, and it's not homogeneous. You're kind of forced to use method of variation parameters. There's not a lot of choices there. Now, one other thing we should note before we get going too far, of course, we're going to get excited, and we don't want to get too excited before we say, hey, what are we looking for? It's telling us to find a particular solution. What a great word, a. It means we just need to find one. That means we're not looking for the general solution. We're not looking for a solution which satisfies particular initial conditions. We're just looking for one solution. And in particular, we would call this in our normal terminology x sub p. So that's what we're looking for. Now, how do we do it? Now, there's two ways to do variation of parameters. Well, one way is you say, okay, we know our function is some combination of our homogeneous things, and that leads to a system of equations that we solve. The second way is there's a formula, and they were nice. They gave us the formula. Wow, what nice people. Mathematicians are just the nicest people you'll ever meet. They want you to succeed because they have problems, but they want you to solve them. All right, so we have this beautiful formula, but then there's all these symbols here. And of course, we know what integration means, but there's this x1, there's the x2, there's f, there's w. We need to go through and make sure we understand what all these pieces are. And once we do, we'll put them all together, and life will be good. So we're going to, first off, get through what do all these things represent. So first off, let's start with x1, x2, because those are the most important. And those come from the solutions to the homogeneous problem. So we start with our solution to our homogeneous problem, and we say that's a e to the 3t plus b t e to the 3t. So what we can do is we can say, all right, we'll let x1 be our first solution and x2 be our second. Now you might say, could I have made this one x1 and that one x2? Absolutely. You'd still get the same answer. So why did you choose that? Well, this one came first. That was the only reason. All right, well, that wasn't so bad. Next, let's talk about f. And what f is f is the function over here. Now, there is one small thing you should always check, and that is, in order for this to be the right f, you look at the coefficient of x double prime. If the coefficient of x double prime is 1, then yes, that's what we have, and it is in this case. If there was something else in front of the x double prime, we say, oh, divide through by whatever's in front of x double prime first, and then you have f. So, not that they would ever do that. Or would they? Probably not. They're not that mean, right? Right? Come on. We're nice people. Okay, so we just copy. So 3t to the minus 5/2 e to the 3t. All right, wonderful. Great progress. And I think the last thing is we got to talk about this W. W must be for like winning, like woohoo, we're winning, yeah! Well, actually, no, in this case it stands for Wronskian. So it's the Wronskian of the two functions. So we're going to say that W of x1, x2, we have to remember how we do Wronskian. And so this is Wronskian of functions. Remember, there's two kinds of Wronskians. You have the Wronskian for just normal functions, and then the Wronskian which comes in for vectors. For functions, the way you do it is you write the functions down in the first row. All right, e to the 3t, t e to the 3t. And then in the second row, you take the determinants. The determinant of e to the 3t would be 3e to the 3t. And then we have the determinant of t e to the 3t, and I think this is probably the place that most people might make a mistake. So be careful here. Product rule, root of the first times the second, e to the 3t, plus the first times the root of the second. Well, that's going to be 3t e to the 3t. All right, kind of barely squeezed it in, but all right. So do our determinant, e to the 3t times e to the 3t plus 3t e to the 3t. And then we're going to subtract here 3 e to the 3t times t e to the 3t. All right, great. Now, we probably want to clean that up, especially because it's downstairs. So you want to make it as clean as you can. And the great thing is it's going to be really, really clean. So notice we have e to the 3t times e to the 3t. And we can either combine it as e to the 6t or leave it as e to the 3t times e to the 3t, either way. Then we have e to the 3t times 3t e to the 3t. But notice here we have minus 3 e to the 3t t e to the 3t, which means that those two pieces here, these cancel. And so that's the Wronskian. Clean, clean. We like a nice clean Wronskian. Well, now what? Well, now we're ready to actually do our formula. Okay, so here are our notes we'll get to refer to as we go forward. And, well, looking at this expression, we have two integrals. So let's just do it in two steps. So we'll call this number 1. Here we go with number 1. All right, so just copy minus x1 minus e to the 3t. And then the integral x2 t e to the 3t. Then times f 3t to the minus 5/2 e to the 3t. And divide that by w, e to the 6t. All right, and of course, good notation, you should have the dt on there. Well, we can clean up a little bit, right? E to the 3t, e to the 3t makes e to the 6t, which cancels downstairs. So those all cancel. The 3 can come out, and then don't forget to multiply the t times t to the minus 5/2. And so, if we do all of that, we're going to have minus 3 e to the 3t integral of t to the minus 3/2 dt. Okay, well that's not so bad. In fact, that's an integral that we can actually do, right? Yeah, we can do that integral. What do we do? Well, you add 1 to the exponent, and if you add 1, you'd get minus 1/2, and then do the reciprocal. So what you would have, that would be minus 3 e to the 3t times minus 2 t to the minus 1/2. Now, you might say, hey, do you need a plus c? And the answer is no, because we just need a solution. So we don't need to worry about our plus c. And if we kept our plus c, we'd find the general solution, but we just want a solution. And all right, so what can we write this as? Well, minus 3 minus 2 makes 6. So we can write this as 6 t to the minus 1/2 and e to the power 3t. Okay, now that's integral 1. There's a second integral. Okay, so let's do that one. And we're not going to be very creative. We're going to call that one integral 2. Yeah. Sometimes it's great to be creative in math, but oftentimes it's better just to say, you know what? Let's not be creative. Let's just make sure we get the right answer. There's value to getting the right answer. So number 2. What do we have? We have x2 of t. Well, that's t e to the 3t. And then we're going to have the integral. And then we have x1 e to the 3t times f, which is 3t to the minus 5/2 e to the 3t. And then divide by the Wronskian, e to the 6t dt. Okay, so we can do a couple things. As before, if we look on the inside, we have e to the 3t, e to the 3t, e to the 6t, and those combined all cancel out. And we can pull out the 3 in front. So we now have, this is 3 times t, e to the 3t, and then the integral of t to the minus 5/2 dt. All right. Well, we're in our home stretch. We just have to do that integral. And how do we do it? Well, we add 1 to negative 5/2, which would make negative 3/2, and multiply by the reciprocal, negative 2/3. So negative 2/3 t to negative 3/2. The 3's cancel, and t to the minus 3/2 makes t to the minus 1/2. So we end up with negative 2 t to the minus 1/2 e to the 3t. So finally, we're in the home stretch. The only thing left for us to do is to write down our answer. We see that our particular solution, it's the two integrals added together, which is 6t to the minus 1/2 e to 3t minus 2t to the minus 1/2 e to 3t, giving us a grand total of 4t to the minus 1/2 e to the 3t. And we're done. That's it. That's the answer. Ah, what a lovely answer. What a lovely answer. All right. You know, these variation parameter problems, they're not so bad. Maybe we should have one on the exam. Maybe. Or maybe not. Who knows? We'll all know soon. All right. Next problem. Number 2. Find the solution of x prime equals this matrix 1, 1, 4, 1 times x with x of 0 equals 8, negative 4. So we're solving a system with a matrix, and we have some initial conditions. And when we see this one, we look at this and say, okay, probably the best thing to do whenever you're dealing with a system like this is to pull out the eigenvalue method. So in particular, we're going to look for eigenvalues and eigenvectors, and those are going to give us our basic building blocks for our solutions, and then we put them together. So there's nothing too difficult about the ideas. It's just, work through the process. No need to rush. And so if we call this A, here's our matrix A. Let's first off, we'll take the determinant of A minus lambda I. And our goal is to set this equal to 0. We solve, that gives us our eigenvalues. So this would be our 1 minus lambda, 1, 4, 1 minus lambda, which would become 1 minus lambda squared, right, down the diagonal, and then subtract 4. Well, if you multiply that out, that would be lambda squared minus 2 lambda, and then plus 1 minus 4 makes minus 3. Well, does it factor? And if it doesn't, okay, what can we do? In this case, it does factor. We need two numbers that multiply to produce minus 3, but add to produce minus 2. And so one way to do that is lambda minus 3 and lambda plus 1. You can check. Lambda squared, then plus lambda minus 3 lambda, that's minus 2 lambda, and then minus 3. Okay, so that tells us that our eigenvalues are the following, namely 3 and negative 1. Now, you're going to say, great, we've done the eigenvalues, so it must be done, right? Because it's called the eigenvalue method. Well, now we got to find the eigenvectors. So we have to go through for these two eigenvalues and find the corresponding eigenvectors. So each eigenvalue has an eigenvector pair. So for that, well, we have to do the work. And what are we looking at? Well, let's start with 3. So we're going to put in lambda equals 3. And what we're looking for is we're looking for something where minus 2, 1, 4, minus 2, that's our a minus lambda I, and times some vector ab produces 0, 0. Well, if you write down the equations, this says minus 2a plus b equals 0, and 4a minus 2b equals 0. Those are the same equation. And so, hey, oh, great, well, we don't really need both of them. So we can just say, hey, let's knock it out. And they might say, what do you mean they're the same equation? If you scale this one by minus 2, you get that one. And so it says, oh, if you look, that says b needs to equal 2a. So our our ab vector has the form a2a or a12. For any choice of a, well, of course, choose 1. So remember, we forgot to write this down. This was lambda equals 3. So that says we have 1, 2. And you can check. Take this vector 1, 2, multiply it by 1, 1, 4, 1. You get 1 plus 2 is 3. That's good. It's scaled by 3. And then 4 plus 2 is 6. Again, you scaled by 3. So multiply the vector by the matrix, it should scale. And it does. All right. Well, now do something similar, but with the other eigenvalue. So if we do lambda equals minus 1, what happens? Well, we get 2, 1, 4, 2, AB, and we're trying to solve 0, 0. Well, all right, not too surprising. We end up with a pair of equations, and those pair of equations are, again, they're actually the same equation, right? And so we say, hey, we can knock one out. So we could say in this case that b is minus 2a. So our vector ab looks like a minus 2a, which is a1 minus 2. And again, you can go through it and check, does this actually do what we claim? We claim it's an eigenvector. So if you multiply, 1 minus 2, okay, that's negative 1, scaled by negative 1. And 4 minus 2 is 2, well, that's scaling this by negative 1. So it is the right scaling factor. Now that you've got your eigenvalue, eigenvector pairs, and notice this is the ideal situation, we've got the right number of each. We say, okay, this information translates into telling us that our general solution for x looks like e to the 3t, there's some constant there, c e to the eigenvalue t times eigenvector plus some constant d, and e to the minus t, eigenvalue there, and eigenvector, 1 minus 2. Okay, so that's what our solution will look like. So we found the general solution, we've made fantastic progress, and we still have plenty of space here. Well, good, because what do we need to do next? We need to find the particular solution. Yes, we do. Okay, so here we go. All right, so let's block off some space here. So we have that x of 0 should be our 8, -4. I'm copying down the initial condition. And now we plug it in here. That will be c. E to the 0 is 1. That's nice. 1, 2. Plus d, e to the 0 is 1. 1 minus 2. All right. Or, if you like, this, if we read off the first row and second row, and what we get is two equations. We need c plus d to equal 8, and 2c minus 2d equals -4. Now, notice in that bottom equation, we could go ahead and just divide by 2. So c plus d equals 8, c minus d equals -2. And now we don't even have to do anything fancy. This is easy. Let's add. Like, okay, all right, sure, let's add. And if we add these together, we'll get 2c equals 6. So that tells us, aha, c has to equal 3. Perfect. Well, if c equals 3, c plus d equals 8. And so 3 plus d equals 8, which means d equals 5. So now we know c and d. And we're like, hey, what do you know? We've got c, we've got d. So last thing we do is we plug it in. So we get 3 e to the 3t, 1, 2, plus 5 e to the minus t, 1 minus 2. And we're done. That's it. That's it. That's the answer right there. Woohoo! We did it! We did it! Yes! All right. Well, on to our next problem, right? We got to make sure, it's always good to take a moment to pause and double check your work, but we don't want to take too many victory laps, right? Because we still have more work to do. Number 3. Given A is this matrix, -1, 1, 0, 2, 1, 2, 0, -1, -1, has eigenvalues 1, -1, -1, with 1, 0, -1, and 1, 2, -1, the only eigenvectors, then find the general form for solutions to x prime equals ax. All right. Now notice it says the only eigenvectors. It's a 3 by 3 matrix. How many eigenvectors should we have? We'd like to have 3, but we only have 2, which means we're missing 1. So this is a case of a missing eigenvector. Now, the good news is we know which eigenvalue has the missing eigenvector, because it has to come from a repeated eigenvalue. So -1 is the eigenvalue with the missing eigenvector. So -1 in the language of what the book used is deficient. There's one small twist here. One of these eigenvectors is associated with 1, and one of them is with -1. Which is which? And are you sure? Yeah. They did something to us here. Well, what did they do? What happened here is that they didn't tell us. How can we figure out? How do I know if this eigenvalue is associated with +1 or -1? And the answer is, we just check. And so here's our check. We do -1, 1, 0, 2, 1, 2, 0, -1, -1. And here we'll do 1, 0, -1. And we see, okay, so we'll get -1 plus 0, -1, which is -1, 2, 0, -2, 0, 0, 0, plus 1. And we say, aha, this is the -1 eigenvector. And when I say the -1 eigenvector, the eigenvector associated with the eigenvalue for -1. And just because, we're paranoid, we'll check the other one as well. So 1, 2, -1. Okay, so we'd have -1 plus 2 plus 0. 1, 2, and 2, and minus 2, 2, 0, minus 2, plus 1, which is minus 1. See, aha, it's the same thing. So this is the 1 eigenvector. And another way to phrase that, it's the eigenvector associated with 1. All right, so what we need to do now is to say, all right, this is our key one. We're going to key off of this eigenvector. So we're going to take a minus 1i, and which is, so it's plus 1 on the diagonal. So it's 0, 1, 0, 2, 2, 2, 0, minus 1, 0. All right, so there's our a minus lambda I. And what do we need? Well, we need the following. We need some a minus on I, we'll call it a plus I, times some vector, let's say u1, u2, u3, equals, and we need to go with the minus 1 eigenvector, and that's this one right here, minus 1, 0, plus 1. All right. Well, this is going to set up a system of equations. And, okay, so in particular, if we think of this as augmented matrix, we have 0, 1, 0, minus 1, and our 2, 2, 2, 0, and our 0, minus 1, 0, plus 1. Well, this is an unusually simple thing to note. What has to be true, we get right away, aha, u2 has no choice. u2 has to be minus 1. And then what happens? Well, we have 2u1 plus 2u2, which is minus 2, and then plus 2u3 has to equal 0. And now, any choice of u1 and u3 that satisfies this solution works. And there's lots of them, infinitely many choices. So we say, okay, let's just pick something easy. If we pick u1 to be 1 and u3 to be 0, that works. So we say, aha, we're in luck. We can choose the vector 1 and 1, minus 1, 0. And we have what we need. Now, what do we have? Well, we're after the general form for the solution. So we can write it as 3 parts. We'll start with the eigenvector for 1, because that, well, there's no surprise. So it's some constant c, e to the 1t times 1, 2, minus 1. And then we can start with the eigenvector associated with minus 1. So that's some constant d, e to the minus t, minus 1, 0, 1. Whoops. Well, I should have copied from there. Both of these work, but 1, 0, minus 1. All right. So these are our freebies in some sense. In other words, even if we hadn't done anything else, we could have just copied once we knew which eigenvalue was associated with which eigenvector. And now we say, okay, our last piece came from bumping up our eigenvector associated with our eigenvalue negative 1. So we have some constant e to the negative t, and we're going to take our well, now we have to be careful because I chose this negative 1, 0, 1, and so if we bumped up from negative 1, 0, 1, we've got to go to there. So, all right, that's a little faux pas on my part, but it's all right. It's still perfectly fine. And all right, so we would have our t minus 1, 0, 1 plus our vector u, 1, minus 1, 0. And there we go. That's our answer. Now, all right, since I made a slight faux pas, I would point out that if I hadn't made this faux pas, we could have also used, and this is probably what we should have done if we were paying attention. You know, this is what happens when I'm not paying attention. Namely, we could have used t1, 0, minus 1. And if we negate this vector when we do the computation, well, we just need to negate our answer. So it would have been our minus 1, 1, 0. And you might say, wait, does that still work? Well, yeah, essentially what we've done is we just pulled a minus out. And we can pull a minus out and absorb it into E, right? Because E is like a sponge, so it can absorb a minus sign. No problem. No problem. Yeah. I am so sorry. This is what happens when you get so excited, you know. But either one is actually an eigenvector, because the truth is there's lots of eigenvectors because you can always scale. But, well, all right. Halfway point. We're done with the first three. So now it's going downhill, right? Yeah. All right, good. So next problem. For the system x prime equals ax, we have both x of t equals this solution and x of t, which is that, a solution, are solutions. Oh, okay. So we've been given two solutions. Find the solution to x prime equals ax with x of 0 is negative 3, 5. All right. So what do we do? Now, there's a couple ways we can do this. And it really just depends on what you're feeling like. So let me talk about some strategies you can take. So one way you can do this is you can say, okay, you could let phi of t be the following. You can construct a matrix. You can do t e to the t plus 4e to the t minus t e to the t minus 5e to the t and minus t e to the t minus 3e to the t e to the t plus 4e to the t. In other words, once you have some solutions, then you say, oh, construct the matrix where the columns are solutions. And that's fine. Now, you might say, are we sure this is good? And we strongly suspect it is because they gave us two solutions. We should expect it came from a 2x2 system. We don't actually know what A is. How do we know it's a 2x2 system? Well, because there's two entries here. And so we should expect that these are linearly independent. Now we're like, okay, great, there's phi of t. And what you can do at this point is you could compute phi of t, phi 0, inverse, and x0, and carry out that computation. And that would work. Nothing wrong with that. Now, the other way to do it is to really just say the same thing, but in different language, which is to say, oh, okay, if I have two solutions, then I should have some combination of them should produce other solutions. So what we can do is we can say, okay, well, let's start by thinking about this as a combination. I have some a, t e to the t, plus 4e to the t, minus t e to the t, minus 5e to the t, plus some b, minus t e to the t, minus 3e to the t, t e to the t, plus 4e to the t. And we're just like, okay, now we just have to solve for a and b. Well, we know what x of 0 is. We know that's negative 3, 5. So that's a for negative 5 plus b, negative 3, 4. And now we have our ideal scenario. Two equations, two unknowns. And, well, in particular, 4a minus 3b needs to equal minus 3, and minus 5a plus 4b should equal positive 5. It's not so easy to combine these together, is it? Maybe. I don't know. One thing we can do is, suppose we say, let's make it a goal to cancel the b's. Well, then let's make what's in front of the b's look the same. So if I have minus 3 and plus 4, multiply by 4 and by 3, and add, we'll get 4 times 4 is 16a. 3 minus 5 is minus 15a. So we'd end up with, let me move this up a little bit. We'd end up with a minus 12b plus 12b, 0, minus 12, and then plus 15 would make this 3. So we're like, that's not so bad. A is 3. Perfect. And now we're kind of in the home stretch in a sense. If a equals 3, plug it in, and we can conclude 12 minus 3 times b equals minus 3. Well, we just swap the roles here, and we get 15 equals 3 times b, or b equals 5. And that gives us our final answer, because that gives us a and b. And so our final answer is we have ourselves 3 times t e to the t plus 4 e to the t minus t e to the t minus 5 e to the t plus 5 minus t e to the t minus 3 e to the t e to the t plus 4 e to the t. And there we go. That's great. Now, like I said, we could do that if we wanted to. Suppose we wanted to go in the route where we will use phi 0 inverse x0. Well, what would have happened there? So, might as well. We're doing great with time. So first off, what is phi 0? Well, plug in t equals 0. Anything with a t in front goes away. So you have 4, negative 5, negative 3, positive 4. And now we want to do the inverse of that. And then we're going to times it by x0, which is negative 3, 5. Well, to do the inverse of a matrix, you can do it in a couple ways, but there's a nice formula, right? Where you take 1 over the determinant. Well, the determinant is 16 minus 15. So that's 1 over 1. And then you swap 4, 4. And then you change the signs. 3, 5. And so that's negative 3, 5. So that's doing the inverse by using the memorizing the formula. And 1 over 1, we don't need to worry about that. And so what do we end up with? We have minus 12 plus 15 is 3. And minus 15 plus 20 is 5. So we say, oh, okay. So to get our answer, we'd multiply phi of t by 3, 5. Which means, if you remember how we do multiplication, that would be 3 times the first column, which is what we have, and 5 times the second column, which is what we have. Okay, so either way, you get the same answer. So there are options. Sometimes it'll say explicitly use phi of t, and sometimes it won't. Generally speaking, do what you're comfortable with, right? We want you to be comfortable. Taking an exam should be a relaxing experience. All right, well, 2 problems left. And we haven't even gone to pull out our Laplace formula table. But, I think that's about to change. Aha! Yes, it is. Given x double prime minus 3x prime plus 2x is f of t, x of 0 equals 0, x prime of 0 equals 1, and x of s equals the Laplace transform of x of t is this expression. S cubed plus 4s squared minus 26s plus 20, s times s minus 1 times s minus 2 cubed. Determine f of t. Okay, so what's happened here? Well, there's some function f of t where this is a true statement. And the problem is asking us, well, what is the function of f of t that does that? So how do we find it? There are two routes. So let's just quickly go over our possible game plans. And what are they? Well, one approach is to say we move forward and solve for x of t. And then once we have x of t, right, because we have this expression, so we can do partial fractions decomposition on it, actually find x of t, and then we can plug in for our f of t. So see, if I have x of t, I just plug it into this expression, and that'll give me f of t. Now, that basically says, hey, you know, we kind of caught this halfway through. Let's finish the problem and solve for x of t, and then once we have x of t, we can go back to the beginning. That sounds like work, especially if you look at this partial fraction decomposition. We're going to have 6 pieces. Let's not do that approach if we have another option. Well, the other option is to sort of reverse engineer. So we sort of run backwards. Say, okay, and we say, all right, let's figure out what went on beforehand. So we could solve for x of t, or we could run it backwards. And that's more where we're going to go. We're going to run this backwards. And what do we mean by run it backwards? So instead of keep going forward, let's sort of jump back to the beginning of the problem and say, what do we have? So we're going to start with our differential equation, and we're going to take the Laplace transform of both sides. So Laplace transform of x double prime minus 3 Laplace transform of x prime plus 2 Laplace transform of x equals, well, something we don't know. Okay, so we can grab our sheet here, and we're talking about taking second derivative. So that would be s squared x of s, subtract s x of 0, which is 0, subtract x prime of 0, which is 1. Okay, so s squared x of s, subtract 1. For the Laplace transform of x prime, it's s x of s, subtract x0, but that's 0. All right, so if we apply those two formulas, we have s squared x of s, subtract 1, minus 3 sx of s, and plus 2x of s. So that's the Laplace transform of f of t. All right. Well, we now say, okay, that's s squared and x squared minus 3s plus 2. So just gathering what's there, times that by x of s is equal to Laplace transform of f of t and subtract 1. All right. And so we see, our x of s is equal to Laplace transform of f of t minus 1 over s squared minus 3s plus 2. Okay, well, all right, except it should be a plus 1. Ah! Because it went to the other side. All right, are we good so far? I think we're doing great. So, if we just pause for a second here, so that's the Laplace transform of f of t plus 1, and we haven't done it yet, but this is if you factor s minus 1 times s minus 2. And that's equal to, well, s cubed plus 4s squared minus 26s plus 20 all over s minus 1, s minus 2 cubed. Now we're like, aha, let's solve. So our goal is we want to solve for that piece right there. So what do? So we can ignore this. We're going to multiply both sides by s minus 1, s minus 2, so we can get rid of our denominators. And we get the following. We say Laplace transform of f of t. So now we're working on getting that by itself. Plus 1. Multiply across. The s minus 1 cancels, and then one of the s minus 2's cancel. So that's our s cubed plus 4s squared minus 26s plus 20. And divide by s times s minus 2 squared. Now this already looks like a much more partial fractions friendly thing to do, right? This one we had 6 pieces. This only has 3. We can live with that, but before we do partial fractions, we've got to handle that plus 1. All right, so what we'll do is we will get rid of it there and subtract 1. So before we do partial fractions, let's put these together. You might say, do we need to? Well, we kind of do. Notice this is s cubed downstairs, s cubed upstairs. So you can either do long division or you can merge stuff together. And, well, let's just merge stuff together. So that's s cubed plus 4s squared minus 26s plus 20 over s times s minus 2 squared. Subtract, well, it's still going to be s times s minus 2 squared. But if we multiply this out, s minus 2 quantity squared would be s squared times s, which makes an s cubed. Then you'd have minus 4s times s, so minus 4s squared, and plus 4 times s, which makes plus 4s. And so we're running out of room downstairs, but that's all right. We have enough room to do one more step down here. So when we put this all together, we see s minus 2 squared, common denominator, s cubed, subtract s cubed, 0. Nice. 4s squared, subtract 4s squared, makes 8s squared, minus 26s, subtract 4s, makes minus 30s, and plus 20. All right, so this is what we need to do partial fractions on. And so this needs to look like something over s plus something over s minus 2 plus something over s minus 2 squared. All right, so good news, we have space. So we're going to use the space. All right, so here we go. Time to do our partial fractions. So we clear our denominators, 8s squared minus 30s plus 20 will be equal to, well, a s minus 2 squared plus b times s minus 2 plus c times s. And let's make some good choices here. S equals 0. If we choose s equals 0, well, 0, 0, 20, 4a, 0, 0, so 20 equals 4a. All right, so that says a equals 5. 2. So if we choose s equals 2, 8 times 4 is 32, minus 60 plus 20. Well, 32 plus 20 is 52. 52 subtract 60 is negative 8. 0, 0, and 2c. So negative 8 equals 2c. Okay, so c should be negative 4. All right, that's actually not a bad thing at all. And anything else? Well, we know A and B now, so anything we pick is a perfectly fine choice. Let's pick 1, right? If we have a choice and we've already picked 0, 1 is our next candidate. 0 and 1 are always like, those are your 2 favorite numbers to work with. You should always pick 0 and 1. All right, so 8 minus 30 plus 20. Well, it's 28 minus 30 makes negative 2. That'll be negative 1 squared, which is 1 times A. So that's 5. Then we're going to get 1 times minus 1. So that's minus B. And then here, we're going to get C times 1. Well, that's minus 4. Okay. And great. Well, 5 minus 4 is 1. We can move it across. And that says, hey, negative B equals negative 1. Which really says B has to equal positive 1. Oops. I can do math. 5 minus 4 is positive 1, but when we subtract, it'll make it negative 3. So B should be positive 3. All right. Double check. It's good. It's a good thing to do. As the great math philosophers would say, check yourself before you wreck yourself. All right, so we have A, B, C. Okay, so we are in our home stretch. So we have come to the conclusion that the Laplace transform of f of t looks like A over s. So that's 5 times 1 over s. And then B over s minus 2. So plus 3, 1 over s minus 2. And then C over s minus 2 squared. So 5 and 1 over s minus 2 squared. And now we take the inverse Laplace. And it's not so hard to do on some of the pieces. So we'd get f of t equals, and now to our table, 1 over s. It's on our table. It's 1. Okay, so that's equal to 5. How about 1 over s minus 2? Well, look here. S minus 2 would be e to the 2t. So, plus 3 e to the 2t. Okay, how about s minus 2 squared? Oh, it's on our table. And so that would be, did I copy something down wrong? I did. I wrote, this shouldn't be plus 5. It's like, there's too many plus 5s here. This should be minus 4. Oh, and after I just said, check yourself. Well, better late than never, right? So, minus 4, and then we'll have t e to the 2t. And that's the answer. There we go. That's it. Wow, cool. That was fun. It kind of, I will say this one is a little bit different here because it's a little, it's sort of like, hey, what was our function that gave us the problem that we have? And so having to figure out what it was, well, not too bad. We can do it. We have the ability. We're smart. All right, well, there's one more. Let's finish it up. Time to bring it home. So, a mass of 1 on a spring with spring constant 9 has an external force of 18 acting on it from 0 to 2 pi, and then a force of 0 at all other times. So, from 0 to 2 pi, there's this, you can think like there's this magnet or something pulling the spring, and then, someone comes along and turns it off. So, all right. So the spring will be springy from that point forward. At time t equals 0, the spring is stretched to 4 units and then released with no initial velocity. So we pull the spring to 4 and then just let go. And now, what's the problem? use the method of Laplace transforms to find a function for the motion of the spring. Express your answer as a piecewise function. All right. Well, this should be fun. Part of the thing that is going to make this one a fun problem is what don't we see? We don't see any formulas. Whoa! That's okay. We have the technology. We have the technology. We can do this. All right. Well, where to begin? Well, let's just figure out what our formula is. We know about masses and springs. We've talked about this. So it's mass of 1. So it's so mass times acceleration. That's part of the force on a spring. And then we have Hooke's law, and there's a spring constant of 9. So plus 9x. There's no damper, so there's no x prime term. The external force is on the other side. Now it tells us we have an external force of 18 initially, and then it turns off. So we'll write that as 18, and then something happens at time 2 pi. So we put this as a unit step function at time 2 pi. And I will say that when they do the unit step function on here, it's really fancy curly. So let's make ours little fancy too. So we're gonna put a little squiggle there. Yeah, look at that. Isn't that a very fancy looking unit step function now? I think it is. Okay, now we're not done yet here, right? Because what happens at time 2 pi? Well, we turn off the external force. So we can think of it as 0 subtract 18, right? Because it was 18, it's going to 0. Or we could just write this more simply as 18 minus 18 times u t minus 2 pi. The good news is this is exactly in the form we need to do our Laplace transforms. What about our initial conditions? Well, we're told we stretch it to 4 units. So we have that x of 0 is equal to 4, and we release it with no initial velocity. So it's not like we stretch and then we like throw it, or we like trying to chuck it somewhere. No, we stretch and release. Boom. So x prime of 0 is 0. That's the no initial velocity. So now we have our formula. So the rest of the problem is solve for x of t, and then once we solve for x of t, we'll be ready to go. So we take the Laplace transform of both sides. So we want the Laplace transform of x double prime plus 9 Laplace transform of x, just going through piece by piece, equals 18 Laplace transform of 1 minus 18 Laplace transform of u t minus 2 pi. All right. Well, we have our reference sheet here, and x double prime, we can handle that. S squared x of s. X of 0 is 4. X prime of 0 is 0. And we don't need to worry about x prime. So that's great. So we write that in. So we're going to have our s squared x of s subtract our s times 4. So I'll write that as 4s. And then plus our 9 x of s equals, here, well, we're going to get 18 times the Laplace transform of 1, which Laplace transform of 1 is 1 over s, and Laplace transform of unit step function t minus a, e to the minus, in our case, a equals 2 pi, s over s. So equals 18 over s minus 18 over s e to the minus 2 pi s. All right. Well, great. We are doing wonderful. So, where do we go? Well, let's add 4s and factor out. So we get s squared plus 9 times x of s is equal to, well, 4s plus 18 over s minus 18 over s e to the minus 2 pi s. and do our division. So xs is 4s over s squared plus 9. We'll leave that alone for the time being. 18 over s times s squared plus 9. We'll work on that. And minus 18 over s times s squared plus 9 e to the minus 2 pi s. All right, well, let's do partial fractions. Now, the nice thing is these are both the same partial fractions problem. So, it's sort of like 2 for the cost of 1. We like that. That's great when we can get a good deal. So let's work through that. 18 over s times s squared plus 9. So that's going to be something over s plus, and cs plus d over s squared plus 9, because this is an irreducible quadratic, so it doesn't factor any further. So we have to have something upstairs that it's compatible with. And okay, we clear our denominators. We'll get 18 is equal to a times s squared plus 9 plus cs plus d times s. Okay, well, we can do something really simple. If we plug in s equals 0, we'll get that 18 is equal to 9a. So that says a has to equal 2. So that's some good information for us to have. So we know what a equals 2. What else can we do? Well, there's not really some other good numbers to plug in. And I know some people are like, oh, go for 3i's. I don't really feel comfortable with complex numbers. They seem complex to me. So let's just expand, since we've used up sort of our easy, low-hanging fruit for plug-in numbers. So if we expand out, well, we have 18. For s squared, we have an a and a c. But we know a. So we get 2 plus c s squared. And then, well, for just s, we have d times s. And then for our constant term, well, we have 9a, which is 9 times 2. Well, we see there's no s squared over here, so this has to equal 0. There's no s term over here, so this has to equal 0. And so, well, that tells us that d equals 0 and c equals negative 2. Now, I just realized, for some reason, I went a, c, d, and not a, b, c. I don't know why I did that. I honestly don't. I'm like, well, why did you do that, Steve? I don't know. They're all letters. Yeah, that's true. They're all letters. Okay, all right. So now we can keep going. C equals. Now, someone's going to be making some video compilation where they're like, 5 hours of me just going all bizarre. Maybe I should just post one and be like, Okay, all right. Back to work. No, gotta be serious. We're in a test. Like poker face. Now, what do we do? Well, the nice thing is we've got some things that are simplifying pretty nicely for us. We're actually doing pretty great. So let's catch up on where we are. So we can say, lo and behold, we really are 2 over s, and then minus 2s over s squared plus 9. All right. So that's what this becomes. So let's put it all together, right? Because we still have these pieces in here. So we have the 4s. So we have x of s. We had the 4s over s squared plus 9. Then here we have plus 2 over s minus 2s over s squared plus 9. And then we have minus, and then we have 2 over s minus 2s over s squared plus 9 e to the minus 2 pi s. All right. Well, that's looking fine. except we're kind of running out of space. Let's call in our next page. Okay, so I'm going to move this up a little bit, and I'm going to copy what we have. Well, almost copy, right? We can put those together. So we have 2s over s squared plus 9 plus 2 over s. And, well, we can go ahead and put the minus sign through. Plus minus 2 over s plus 2s over s squared plus 9. That's a terrible looking s. That's a terrible looking 9. E to the minus 2 pi s. All right, let's move that aside, and let's finish this off. Okay, so now is our time to look at our sheet and say, does this match anything? And we say, hey, this looks an awful lot like cosine. It basically is the cosine, where we have a equals 3. So the s upstairs is good, so we should rewrite it one more time. We pull out the 2. The 1 over s, again, is good. We just pull out the 2. So this should be the same as 2. And I'll write as s over s squared plus 9 plus 2, 1 over s. And then I'll have a minus 2, 1 over s e to the minus 2 pi s. I don't know why I'm getting so excited about parentheses here. But you know what? In for a penny, in for a pound. We're going all the way in, just so we can go through term by term. Now, we're ready. So, we have x of t equals 2. And this part is the cosine. That's what we just talked about. And it's cosine 3t plus 2, and 1 over s, we saw that as well, is 1. All right. Then we have minus 2, and now we come to similar things. 1 over s, we know how to handle that, 1 over s, but notice that we have this exponential function. So now we're looking in particular at this expression. If you have an exponential function attached, it means a shift. Now the good thing is, what are we shifting? We're shifting the function 1. If you shift the function 1, it's still 1. So it's really 1, but times our unit step function at t minus 2 pi. So that e minus as became, we have something turning on and off at t minus 2 pi. Now the same thing will happen here. We're going to have our cosine function. It's actually the same cosine function here, shifted, and we're going to have it be turned on at time 2 pi. So plus 2 cosine 3, and here's the shift. We're going to do this properly, t minus 2 pi, and then our fancy step function t minus 2 pi. All right. Let's clean it up a little bit. Now, notice this part right here is the same as cosine of 3t minus 6 pi. What effect does the minus 6 pi have? So if you think about it in terms of the circle, minus 6 pi means you go backwards 3 times. But because of the circle, every 2 pi you come back to where you were. So this is the same as just cosine of 3t. Now, that's that part. But if we go back to our problem, which I happen to have the problem here, it says, okay, use the method of Laplace transforms. We've been using that to find the motion of the spring, which means x of t. Express your answer as a piecewise function. So we're not quite done. So our goal is to say we want a piecewise function. This is a function not piecewise, but as sort of, you might say, a line expression. So here we go. Piecewise, well, where do we change? So we're looking for something going on and off, which means looking for a step function. So we change at time 2 pi. So we're going to have something happening up to time 2 pi, And then we're going to have things happening after time 2 pi. So before time 2 pi, this last part isn't there. So what we see is the function 2 cosine 3t plus 2. All right, so it's the cosine function, but it's actually been shifted up by 2. So if this is the axis, it's doing this. So it's going down to the axis, but the force acting on it is such that it won't go below. It'll actually just come down and just barely touch. See, normally when we oscillate, we go up and down evenly on both sides. But this external force says just as you hit the axis, you turn around. But our force gets turned off at time 2 pi. Now, what happens there? So at time 2 pi, we have 2 cosine 3t plus 2 minus 2, because this has been turned on, and then plus 2 cosine 3t. Well, the 2's cancel. The 2 cosine combine, and it makes 4 cosine 3t. And that is the answer. And actually, we should just make a note. This isn't required, but it's kind of a cool thing that happens here. So what ends up happening is if we go up to time 2 pi, what we'll see is, like we said, we start here at 4, and then we oscillate up and down. And we'll go through 3 revolutions because of our 3t. Normally 2 pi would give us just 1, but we'll go 3. So we oscillate just barely touching the axis, and height of 4, and down to 0. So that's where we'll go. And then after that, will be 4 cosine 3t. So it'll actually still stay the same height, but now it'll go below the axis. And so that's the picture. So up until 2 pi, our force, which should be, think of acting upstairs, it's pulling it up so far, it never goes below the axis, that's like you said, and it goes forward like that. All right, well, whew, done. And I know you're looking at the time like, wow, we are getting dangerously close to the length of the actual exams. Are we going to succeed? Yes, we believe in you. Some of the problems that we've put on the practice exams are more challenging than what we will see on the real exam. But by doing these problems, you're building your mathematical muscles. You know, like, look at the size of those mathematical muscles that you have. Now, my gosh, you're just going to go in there and you're going to do great. I believe in you. Good luck, and thanks for coming and doing some practice. All right, bye.